Hi, good morning, everyone. Could everyone hear me clearly?
Yes, we are.
Yes, we can. Yes.
I would like to just first acknowledge that it's a great opportunity to be able to be here virtually, live, to make this presentation at this conference. My name is Leticia, and I will be presenting to you, as mentioned before, a goodness of fit for probabilistic models in terms of electric vehicle charging behavior. Now, in 2018, the EIA stated that 28% of US energy consumption is used for transportation, while 92% of that value is actually supplied by petroleum. This is quite an alarming figure. And in order to reduce our carbon footprint and increase our energy efficiency, we need to find sustainable alternatives to internal combustion engines. Plug-in electric vehicles actually provide a viable solution. They draw electricity from batteries and could be charged from external sources. There are various types, but the two main types that we'll focus on are the battery electric vehicles and the plug-in hybrid electric vehicles. The BEVs, or just EVs as they are known, use a battery to power an electric motor powered by the grids, and the PEVs use a battery in conjunction with an internal combustion engine in cases where the battery power is depleted. Now, in terms of EV deployment, it has grown quite drastically over the past few years. And this has actually posed a problem for the charging infrastructure. And that's actually a key challenge with respect to the transition to electric mobility. Of course, Podolsky and Arabi in 2011 stated that it would have a huge impact on the electrical power grids. So Green et al. Looked at the factors impacting these electric grids, some of which are stated as shown. Some of the main ones would be the vehicle demand profiles in terms of the charging characteristics, the charging timing, and of course, the vehicle penetration into the market. In terms of the charging station load, we actually acknowledge as well that these could have quite an impact on the longevity of these grids. Now, in terms of the actual charging behaviors, uncoordinated charging is one of the main issues. It's a clustering or herd effect where basically persons are all charging their vehicles at the same time. And Murray in 2013 actually stated that this could have a toll on the electric system infrastructure because increased EV penetration, of course, will cause voltage imbalances and outages. So we realize that there is a significant need for a more controlled or coordinated charging strategy using smart systems by the way of smart grids. And smart grids would actually enable the users to be able to plug in their vehicles at specific times to charge and not all overload the grid at the same time. So of course, in this particular instance, we could see that electric vehicles could be a grid asset, but only with planning and investment. So in terms of finding that well-coordinated charging strategy, we have certain requirements of such a scheme. We would need to have real data, and of course, we would need some driver behavioral variables to perform simulations to be able to come up with such a strategy. But of course, as we know as researchers, it's quite difficult in certain cases to get data. It's very scarce, and probability distribution functions actually could provide a means of looking at some of these driver random variables, And that's the mechanism we use for our research today. Some fairly recent research in this area is by the three authors that I have stated on the screen. They all looked at probabilistic models in different arenas, one to assess the impact of the grids, one to look at the EV charging profiles, and of course, there's also a stochastic model for driver variables by Almaturi and et al. In 2018. So therefore, this draws us to the motivation and the objectives for our study. We want to look at some exploratory and inferential analysis of probabilistic models for EV charging stations and residential load profiles. And specifically, we'll generate some descriptive statistics. We'll construct aggregate load profiles by day of the week. And we'll also look at the goodness of fit to be able to deduce which of these PDFs actually have the best fit. The methodology we use is a PDF fitting case study based on the REX dataset, which has 348 vehicles for 200 randomly chosen households. It includes some energy characteristics And we also have things like the household demographics and usage patterns. So this data set is used to perform simulations which actually have the residential power profiles and the in-home recharging profiles validated by meter data. The data is extremely granular. It's about 10-minute resolutions over an entire year. Some of the assumptions with respect to the vehicle ranges as stated, as well as the assumptions with respect to the levels of charging, level 1 and level 2. In our particular data set, we just chose to look at the level 1 charging, which is usually the level of charging for in-home charging. Now, in terms of those two data sets, Muraturi et al. In 2018 used them in a behavioral model to construct what we call a residential energy ecosystem model. So you could see the REX data set came into play in the power demand model. Now, this power demand model for residential households is actually very variable because, of course, it's stochastic. Most of us don't charge or have the same behaviors at the same time in terms of our power usage. And then we have the personal energy demand model, which is actually simulations of the amount of energy to be able to fully charge the battery. So how does this come into play? Well, in our research, we were able to extract these two data sets, and using our statistical software, we had to match the EVs to the households. We wanted to create load profiles, so we did some aggregate household load profiles based on the equation shown, which is the sum of the base load and the total EV loads per household. We created these load profiles in an aggregate sense with respect to hours in a particular day. And we use software to be able to find the parameters for the probability density functions that we're going to look at. So it's basically a maximum likelihood estimation method, which uses an iterative parameter estimation. So the three best PDFs for these, in terms of a preset database, the Excel Stat software has about 55 PDFs. So we actually were able to choose the top 3 based on that. Now, in terms of the goodness of fit, now the goodness of fit is actually just the overall fit of the model to the original data. So we wanted to perform some inferential tests to look at the if the data actually follow the specific distribution that we choose. So in terms of this test, we use a robust non-parametric test called the Kolmogorov-Smirnov test. And this particular test has certain criteria in terms of the sensitivity to shape and scale parameters, which is vital for analysis. The criteria with respect to the actual hypotheses and accepting or rejecting are shown. We use a significance level of 5%. So we would reject the hypothesis if it is that the value was less than 5%. And of course, we would choose the PDF with the lowest value among others to determine the one with the best fit. The top 3 PDFs that we were going to look at in terms of our research in particular, the Johnson SB, the generalized gamma and the Dagum functions. Now, just to give you all a brief snapshot of some of the exploratory analysis in terms of visualizations, this is actually a view of the load profiles by the time of day. And we could see, of course, the peak demand between 4 and 10 p.m. daily, as we would expect, because most of us would probably come home from work and want to charge our vehicles at that particular time. And of course, the off-peak times are between 2 a.m. and about 5 a.m. If we want to build a coordinated strategy based on this uncoordinated clustering effect, we would want to, I think most of us would be quite familiar with the term flatten the curve. So we would want to try to look into flattening the curve with respect to those peak demand times. Some descriptive statistics I'll just go through quickly. Basically, we have the mean loads for the days of the week, which we aggregated here, and we could see most of the days of the week had similar loads, Tuesday being the highest and Thursday being the lowest. And we also constructed some mean loads for weekday and weekend. We also look at taking the weekly load and actually having an aggregate value for the peak demand and for the off-peak demand by weekday. And this particular artifact is actually very interesting because we could use it in time of use tariffs to actually incentivize persons who want to join, to actually charge when it's off-peak periods. Now, in terms of the PDFs, these are the actual PDFs stated here for the functions that I mentioned before. And these PDFs actually give an idea of the, we generate the power demand, which is f of x, at a specific charging time X. Why these PDFs are important is that they actually have different flexibilities in terms of the scale and shape parameters. Now, in terms of our analysis with the inferential statistics, we could see that the PDFs here, the Johnson SP PDF is actually the one that came out to have the best fit out of these 3 particular PDFs. These are the parameters I've stated here below the graph, and the graph itself actually gives you the PDFs. I know they are pretty close in certain areas. You may see some overestimates and underestimates as well, where the empirical values are actually in the histogram. And this actually gives us an idea of the fit of these particular PDFs. Please note that this is just from a preset database that Excel provided, but you could also have, there are hundreds of other PDFs that may be able to provide a better fit, and we could actually tweak the parameters to make it a more accurate fit for our data. So in conclusion, we could see that the EV charging characteristics can actually be described using probability distributions. We estimated the fitted PDFs for the uncoordinated charging schemes with respect to those household load profiles. Of course, as I mentioned, the shape and scale parameters could be adjusted and altered, which is a main advantage as opposed to the usual distributions such as the normal and Weibull distributions. Then we could actually use these PDFs for other driver variables like arrival time, state of charge, daily mileage, etc. By geographic locations and seasons. And of course, the future of this would be to create coordinated charging schemes and use it in demand side management, which would actually improve our power consumption and help in our development of smart grids. So here are some of my references, and I thank you very much for your time and attention. Are there any questions?
Thank you very much, Leticia. Appreciate that. So we have 2 questions that came in on the chat, or 3. Let me start with these 2 easy ones for you. The first one is, what do you mean by probabilistic? And the second is, why did you decide to use a probabilistic model type?
Those are excellent questions. So probabilistic means that there's some uncertainty or randomness. And as we could appreciate in terms of the world, although we use deterministic methods for a lot of things where we have set parameters for certain processes and functions, probabilistic means there's some kind of likelihood that something may occur. As I said, our behavior is stochastic, it's random, and the word stochastic actually means there's a probability attached. So because of that, and because of the fact that our behavior is random from person to person in terms of our charging behaviors as well, we decided to use probabilistic models in that sense, as opposed to a normal deterministic model. Could you repeat, Dr. Bahadur Singh, the second part of the question?
First one part was, what do you mean by probabilistic? And the second part was, why did you decide to use a probabilistic model? So I think you have more or less captured that there.
Yes, I hope I did.
Yes, I think so too. I have another question here. Was the Raleigh PDF ruled out in previous studies?
Okay, so that's a good question. Actually, in previous studies, we have a number of other PDFs. Some of you may know the Weibull distribution, the log normal distribution. The Raleigh was also one as well. So what's important here is that if I were to do this for, in some research, if you do this for other driver behavioral variables, you would see the Raleigh may come up as the more applicable PDF in terms of the hypothesis test. It really is based on the data set and the behavior of the data in that sense. So I would say that it's not ruled out. It's just based on the actual behavior of the data and the way the trends work with respect to that data.
Okay, thanks. I have another question. Did the models account for the age of the battery?
In this particular one, no. But one of the main assumptions, which was really from the work of Muratori in 2013, is that he actually assumed that the battery would be going from 0 to 100 in terms of charge. Now, I know usually people don't wait till their battery dies to charge it, but that was one of the main assumptions here. So we didn't take into account the age of the battery, but the time of charge in terms of the percentage charge was an assumption.
Also to add to that, we did not have that information. And the
Yes.
last question, why not adopt a machine learning approach?
Right. I like that question, actually. That is what we are moving towards. So we basically wanted to look at the behavior. I'm a statistician by nature. So I really wanted to look in terms of the density functions and see how they are applicable here, because a lot of work hasn't been done there. But we are moving towards a machine learning approach. Now, as you would appreciate, because of the scarcity of data, and especially in terms of like Caribbean countries, for instance, we don't have a lot of data. So we have to look toward the larger countries and the behavior of their data sets to see what could be done. So we try to look at that and basically try to have an idea to be able to model. So machine learning is something we are actually working on right now and we are moving towards.
Great, great. Thank you very much, Leticia. Appreciate that. That was a very clear presentation, and thank you for taking